Thank you, Lucas, for introduction. Thank you for being here today. Is it working? Can you hear? Okay. Again, thank you for being here today with me to talk about how to run and write effective Docker-based tests in Scala. My name is Matteo. I work as a software engineer at Kinetics, where I take part in the design and development of different types of applications, from embedded to cloud and distributed. And sometimes I also act as a DevOps engineer, and this has given me the opportunity to see how different testing is in different contexts and different types of applications. And I've also been writing Scala code for roughly 4 years on and off now. So we'll start this presentation talking about why testing is really important in modern software. And then we'll move to see how we can write Docker-based tests in Scala. We'll see two alternatives for this: sbt-docker-compose, which is an SPT plugin, and testcontainers-scala, which is a Scala wrapper of a Java library. And in the end, we'll conclude with a brief comparison with two technologies. So first of all, why is testing so important nowadays in modern software? Well, when I just got out of university 5 years ago, I thought that I knew the answer. I would say that testing is important because it's the way that software engineers and developers use to make sure that their applications are behaving correctly, the way they're meant to behave. But this is not it. This is just one side of the coin, because if you think of testing in these terms, you can just write messy test code. This is what happened to me. I wouldn't pay the same attention to testing code that I paid in writing application code. And so I ended up with messy tests that were difficult to read, difficult to maintain, difficult to refactor and understand in the long run. And this is because testing is important for two more reasons. The first one is refactoring. It is very difficult to refactor an application, and believe me, I've been there, if you have no automated tests at all, or if you cannot trust your tests. Because as soon as you start touching your code, you have no way of understanding if you are breaking something, because you have no confidence in your tests. And so this gives you less confidence in fixing bugs, and also in less confidence in developing new features, because you cannot trust your tests, you cannot trust your code base. And the more tests you add, the more code you add, the more difficult it becomes to add new tests. All right. The second main reason is documentation. How many times as developers have we landed, for example, on a GitHub page, and in the README, we would read something like, if you want to see more examples about this library, just look into the tests. Now, if our tests are badly written, the users of our libraries, the possible future users of our libraries, will just run away because they cannot understand how to use our software. This is to say that if we don't pay attention to our tests, the maintenance cost of our code base, and also the cost of extending, of adding new features to our code base, increases over time. And the more code we add, the more tests we add, and the more it becomes difficult to maintain our code. But of course, testing nowadays is complex because we have tons of different types of tests. Now, this is the testing pyramid. Some of you probably have seen it already. It basically describes the different types of tests that we can find in a code base. Now, everybody has their own favorite version. This is mine. It's very simple. At the very bottom, we have unit tests. Now, they should be the simplest and also the fastest because they only verify the behavior of units of code in isolation with no dependencies, with no additional complexity. The higher we go in the pyramid, the more complex tests become because we start adding to the picture interactions among different components, dependencies of different components. The more dependencies we add, the more complex the testing becomes until we arrive to end-to-end testing or system testing, where we verify the behavior of the application as a whole, if it fulfills our use cases or not. And of course, nowadays, our software has tons of dependencies, not only within our code base, but also on the infrastructure, on the services that we use. For example, it is very common for our application to depend on other applications, such as microservices. it is very common for our application to depend on a database or on a file storage system such as S3 or on a caching system such as Redis. And so the problem becomes, how can we test our application in presence of these third-party infrastructural dependencies? How can we make sure that our application, that our software will behave correctly in a production-like environment? Now, historically, developers have been using in-memory alternatives to fix this problem, to solve this problem. For example, we could use an in-memory implementation of a database, such as H2. We can use the file system to store files and also to act as a cache, but this doesn't give us the level of confidence on our software that it will behave properly in the production environment, because we are not testing our software with our production dependencies. And so in this case, Docker comes to the rescue. For the purpose of this presentation, Docker and Docker images are basically just a way for us to package software with all the libraries the software needs in order to run. And when we run an image, we get a Docker container. So for example, we can have a MySQL container. If we have a MySQL dependency in our infrastructure, we can have an S3 container, a Redis container, and we can have containers mocking the other applications, the other microservices that we are using. And so in this context, Docker containers, these running Docker images, they just become test doubles, mocks. We can use them in our testing pipeline, in our testing environment, to have a greater level of confidence that our application will behave properly once deployed in a production environment. Now, of course, this is suitable from integration tests above, because unit tests, they do not test any dependencies, any complexity. But from integration tests above, we start testing the integration of our application with these infrastructural dependencies. Now, based on my experience in Scala, we have 4 different ways to do this. The first one is also the simplest, and it only involves manually writing Docker commands. Now, we can open a shell, for example, run a Docker command to run a container, write a shell script to run more than one containers sequentially as a whole, and also use Docker-compose, which is essentially the same thing, but we just describe our containers in YAML syntax. Now, all these different approaches, they suffer from one main problem, which is code duplication. Now, as developers, we know that code duplication is evil. It's bad. We want to avoid that at all costs. But if we start using shell scripts or Docker-compose to describe our containers, now we have the configuration of those containers duplicated in the Docker-compose file, in the shell script, and in our testing code. And now in the long run, this code duplication leads to inconsistencies, which makes our code more difficult to reuse in different environments, to be automated, and so on. So what's the solution? The most immediate solution for us as developers is to just manually wrap these Docker commands and run them in our testing software. Now, at Kinetics, we had a project doing this. So in our testing classes, we would also take care of configuring the containers, running the containers, and destroying the containers, wrapping essentially Docker commands. This is bad. It is very bad because even though it solves the code duplication issues, now we have a bad problem, a very bad problem, which is double responsibility. Our testing components are not only responsible for testing the application, for verifying that the application behaves correctly, but they also have to configure, run, and kill our containers. So in the long run, this becomes very difficult to maintain, because if we need to add a dependency, we need to extend our testing classes to support yet once more container, its configuration, its creation, and its destruction. So what's the solution? The solution is to not reinvent the wheel, to let third-party frameworks or libraries do this work for us, take care of this work for us. This is what both sbt-docker-compose and testcontainers do. The former is an SBT plugin that essentially wraps a Docker Compose file. And the second is a Java library that gives us a very low-level, fine-grained configuration over our containers. We'll see them both with some code examples in this presentation and compare them at the end. For us, our case study will be a very simple Scala application. This is Scala free code. Essentially, the application just opens a connection, listens on port 8080 for incoming connections, and for each incoming connection, it just replies with a very simple web page with only the string hello Madrid in it. So the application is very simple, very basic, but it is complex enough for us to see how different the testing code is using sbt-docker-compose and test containers. So we don't need anything more complicated than this to assess the difference in the design of these two technologies. Let's start with sbt-docker-compose. Now, this is an SBT plugin, so we are coupling ourselves with SBT, which is fairly popular and fairly widely used, but this is not the only Scala build system, so we need to be aware of this. That essentially wraps the execution of a Docker Compose file. We have to list all of our images, all our dependencies in Docker Compose file, and then the plugin will take care of taking these images and running containers for us, publishing the port mappings for us to access them in Scala test, for example, or in our testing framework. The problem with this plugin is that, as we'll see, it is cumbersome to configure. We have code duplication, again, because some information, as we'll see, has to be duplicated in the Docker Compose file and in the testing code. But probably the main showstopper is that it is not maintained anymore. Now, this is not a very big issue, but it is an issue. There are many forks of this project on GitHub. We as Kinetics had to fork it to support the version 2 of Docker Compose. So it is still usable. We use it for 2 years, but we have to put some effort to maintain it if we want to use it in our code bases. Generally speaking, the flow only involves publishing a Docker image tagged with the latest. Now, the latest in Docker is a standard tag to publish the latest version of our image, the most recent. This is to avoid, again, code duplication. We want to avoid hard coding the version number of our application also in Docker Compose file. Then we create a jar with all the test files, and we run it using a dedicated SBT task, which is Docker Compose test. Now, this is quite bad because we cannot use, in a simple way, the usual tasks that we can use in SBT, such as test or test only. And also, we cannot use the usual IDE buttons to run tests. So with this technology, it is very complex to run a single test in isolation, a single test in our test base, because what the plugin essentially does is it takes the Docker Compose file, run all the containers, and reuse those containers for all our tests. So it is very difficult to run a single test or to debug a test because we have to add additional configuration to our build system to run single tests or to debug them. As I said, the plugin reuses the same instance of the containers for all the tests in our code base. On the one hand, this is a good thing performance-wise because we don't have to start Docker containers over and over again. Docker containers, as you may know, can be fairly memory intensive and fairly difficult to start. On the other hand, for us as developers, this can be a problem because we have to set up and tear down the containers, their state in each test suite. For example, if you have a database, we have to set it up. Example. Is it better now? Can you hear me? Okay. Okay, so I was saying that as developers, we have to, for example, set up the database for every test suite if we need different tables. And if we write data on it, we have to clean the data up for the other tests to start fresh with a fresh state. So the Docker Compose file for this test is very simple, very standard. We have to specify the name of the service. This is the name of the container eventually. Docker image. So the name of the image, the version with the latest, again, to avoid code duplication as much as possible, and a local bit annotation to avoid pulling the image from a remote repository. And then there is a port mapping. So, okay. Can I go? Okay. We are essentially publishing port 8080 of the container to a random port on our workstation or testing environment for us to send HTTP requests to this container. Now, if the Docker Compose file is simple, the testing suite is very complex. Now, I had to use 2 different slides to fit all the relevant code, and yet it is not all. So this is Scala test. I don't know if you're familiar with it. I will guide you through it anyways. So in Scala test, the way you write test suites is that you create classes and mix in some traits to define the behavior of your testing suites. Now, the first trait we're mixing in is a test trait, a style trait. It defines the way we can write test cases in our test suite. For example, the AnyFun suite lets us write tests with a test method. Different styles require us to specify keywords such as given, when, they adapt to different testing frameworks and testing styles. The fixture prefix means that our test will run with a fixture, and a fixture in software testing is just a context, a state that is passed to any test case for them to run with the same information. In this case, our fixture will be the port mappings. So sbt-docker-compose publishes the port mappings as a fixture for our test. Now, being in Scala, we have to give a type to this fixture, and this is what the second trait does. With config map fixture, we are setting the type of this state to config map, which is a very bad choice because it's a map from string to any. So essentially, this is a JavaScript object, sort of. And as we'll see, we have to make explicit conversions, casts, to extract information from this map. Then there is another bad part, which is eventually. Now, sbt-docker-compose doesn't have any built-in concept of container readiness. So as soon as the containers are running, the test will start running too. But for example, some containers need time to start up. Think of a database, for example. It needs time to create all the relevant schemas, tables, maybe initial data, and so on. And so we have to account for this in our testing code, because sbt-docker-compose will start our tests without waiting for the database to be ready, or for any other container to be ready, for the matter. And so we're using eventually. Eventually, in Scala test, is a trait that is common in eventual consistent systems, because it lets us, as we'll see in a minute, repeat some assertions until they either become true or a certain threshold, a certain number of attempts has been hit. This certain threshold is provided by integration patience, which is a sort of default configuration. Now, in the testing suite, we first fetch the configuration map. This is passed by Scala test, and we use it to extract the host and port information of our container. And then we use eventually. With eventually, we essentially keep sending HTTP requests to our container until it starts responding with, for example, a successful response containing the expected body. This is very bad because in our testing code, we have to cope with a limitation of the framework of the plugin that we are using. This code is very difficult to reuse. It's very unclear too, because in 2 months, if you read eventually, and if your system is not eventual consistent, you will be tempted to just remove eventually, having failures in your tests that you cannot explain, maybe for a new colleague that's not familiar with the system. This is very bad and makes the code very difficult to reuse across different projects. But the worst is yet to come, because the way we have to fetch the port mapping involves, once again, code duplication. Here, to build the key in the configuration map, we have to specify the name of the service, so the name of the container, and its port, the container port. Now, this information is duplicated in the Docker-compose file and in our testing code, making it more difficult to reuse. It is not just this information. Any other configuration, such as passwords, file system bindings, and so on, have to be duplicated in the testing code and in the Docker-compose file. And then again, we use this information to extract the port mapping from the configuration map. This is very low-level code. We check if the key is defined in the map. If it is, we extract it. We explicitly turn it into a string, because once again, the value is here as any. And then if not, we just throw an exception. Now, this is, again, code that we don't want to write in every suite in our projects. This is low-level code, and our framework, the library, should take care of this. Now, the code here is very verbose. There is a lot of boilerplate, but the entire system works. It works just fine. If you are OK with these limitations, you can use this plugin, and we did for a couple of years. Then we figured out about test containers, and early in January, we started migrating all our projects that we're using sbt-docker-compose to test containers. Now, test containers is originally a Java library that gives us a very low-level and fine-grained configuration over our containers. For example, we can choose if we want our containers to run for each suite. So each suite will have its own containers, or each test case will have its own containers. Now, this is nice because different test cases might have different requirements. And of course, having fresh containers for each test case frees us from the issue of cleaning them up. We don't have to clean up their state anymore because we know that each different test case will have different containers. On the other hand, performance-wise, this can be bad because Docker containers can be, again, memory-intensive. Starting them up for each test case takes time. And so generally, testcontainers-scala is a little bit slower than sbt-docker-compose in the execution time, in the testing time. But as we'll see, the code that it produces is much more readable. The flow is simpler too, because we can now handle anything in our code, in our testing code. We don't have code duplication anymore. We can optionally configure SBT to publish the information about the Docker image, its name and version, for example, in an environment variable that we can read in our tests. Again, we can configure the SBT tasks to always build a Docker image before starting, and then we can use these SBT tasks to run our tests. So we don't have dedicated tasks anymore. We can use test and test only, and again, we can use our IDE buttons to run our tests. So this is very good, because if we just want to run a single test or a single test case, we can with test containers. It is very simple. We could not, or it was very difficult with sbt-docker-compose. In this library, everything is built around the concept of a container definition. Now, if you're familiar with Docker or Docker-compose, a container definition is essentially the same thing done programmatically. For example, using this generic container constructor, we can specify the name of the Docker image. Once again, see that we are fetching it from an environment variable that is set by SBT. So this way, we avoid code duplication in the name of the Docker image and in the version too. We can specify the exposed ports, in this case, port 8080, used by the container. But most importantly, in test containers, we can specify our waiting strategy. Now, test containers has a built-in concept of container readiness, and lets us specify how we should wait for this container to be ready. For example, we can inspect the logs, or in this case, waiting for the port to return a 200 or 204 code. So we can tell test containers how to wait for the containers to be ready. This way, we don't have to have timeouts or eventually in our testing code anymore. Our testing code will be much simpler. Then, once we have this generic container, this container definition, we can wrap its definition in a class, in a Scala class, such as app container here, and then define a very clean and well-typed interface over the configuration properties of our containers. Now, for example, in this case, we are just publishing the port mapped to port 8080 of the container. But if we had database passwords, root passwords, usernames, and so on, we could add additional methods or additional values to this interface for our test classes to use them. This is much better because we don't have to deal with any anymore. There is no more code duplication. There is just a well-typed interface that we can query whenever we need information about our containers. And then this is the resulting test class. Now it fits a single slide. It fits a single snippet of code. Notice that we don't have that sequence of traits anymore. We don't have any fixture anymore. We just have one single additional trait that specifies the behavior of test containers. In this case, we are saying that we are going to reuse the same instance of the container for each test case. Now, this suite only has one, but in general, if we had more test cases, all those test cases will reuse the same instance of our container. Now, in the test case, we first fetch the instance of the container with the with-containers method, and we use it to query the information about the host and port. Now, host is a built-in method of test containers, whereas port is the one that we defined before. This is our interface. This is what we can use to query information about our running containers. Now, it is worth it to say that test containers has some built-in modules wrapping common containers such as MySQL, MariaDB, Cassandra, and so on. And they provide us with built-in properties that we can use in our test cases. And this is it. This is just the same test as before. It is much simpler, much more reusable. The container definition is a class that we write. We can write a library of container definitions and reuse it across different projects in our organization if we have the same dependencies in different projects. So this is very nice. In conclusion, testing code is very important. And it is very important to put a lot of attention in our testing code because bad tests will negatively impact the performance of our programming workflow. But of course, the testing framework that we choose affects the design and the implementation of our test cases. In this presentation, we saw two different alternatives to integrate Docker containers in our tests. The first one was sbt-docker-compose, an SBT plugin which is abandoned and difficult to use, slightly faster than test containers, but the code it produced was very ugly. There was a lot of boilerplate and was very verbose. On the other hand, we have test containers. Test containers is a Java library, but the code in Scala, there's a Scala wrapper that it produces is much more readable and reusable across different projects. So in conclusion, this is just to say that anytime you need to integrate a new testing library or framework in your code base, do not only look for performance and correctness of this new framework, but also take a look at the resulting code and see if the resulting code is more or less readable than before, because readability and maintainability of the testing code is important too. Because in the end, code smells in the testing code are just as bad that code smells in the production code. Thank you very much.